Welcome to the Epidemiology of Everyday Life lessons. This lesson introduces our first model. Recall from the previous video that models provide a simplified description of the world. In epidemiology, we might be interested in how some risk factor relates to an outcome. For example, does drinking contaminated water lead to cholera? Also recall that we estimate models if we collect our own data. When we collect that data, we observe some variable that measures the risk factor that we call X, and a different variable that measures the outcome that we call Y. But an even simpler model exists that you probably use every week, if not every day. The mean, also known as the average. In statistics, we represent means with a little bar over the variable. We will be measuring outcomes, so we write the bar over the letter Y. But how is it that something as simple as the mean represents a model? That's what we'll be discussing for the rest of this video. Let's start by remembering what our friend George Box may or may not have said. All models are wrong, but some are useful. The key to this is knowing how models are wrong, and that makes them useful. For that reason, we focus on errors. Errors are defined as the difference between a value that we observe in the population and the model's estimate. Imagine that we collected data on how long every student at the university slept last night. After we collected the data, we took the mean, the average, across all university students. And let's suppose that they got, on average, 6.6 hours of sleep last night. That's our mean, Y bar. Now let's suppose that you got 7 hours of sleep last night. We put a little I below the Y to tell us that the value measures just one of the observations in the data. So your YI is 7. The model's estimate of your sleep, therefore, has 0.4 hours of error. And just like your Y has its little I, your E also has its little I. This means that we have as many E's as Y's that are in the data. To measure the value of the EI's, let's start off by simplifying our data to 10 observations. Each dot here represents the amount of sleep one student got last night. The dots are arranged in descending order from the most sleep to the least sleep. On top of these data, we will plot a line with our mean, Y bar, which is equal to 6.6. The distance between the plotted point and the mean represents the error. So each of the orange lines on the screen represents one EI. All of the lines on the screen now represent positive errors because the observed value is greater than the mean. Now we did the same for the negative errors, the observations that are less than the mean. The bars on the left side of the graph represent those errors. Errors 6 through 10 will all be negative because the observed hours of sleep were less than the mean. The mean is special because it balances all of the negative errors with all of the positive errors. Another way of saying the same thing is that the absolute sum of the negative values equals the absolute value of the sum of the positive values. It would also be true that if you lined up the lines end to end, you would have segments of equal lengths on both sides of the mean. Now we get to the formality of the model. The mean provides us with the number that minimizes the error, or another way to say that is the sum of all errors will equal 0. The mean also meets our requirement that we can make an educated guess about values. Because the mean minimizes the error, it will, across the entire population, give us the number most likely to end up close to an actual value for every observation. But the mean does not describe the variance very well. For that, we'll need something else. For the variance, we want to know about how much error we can expect our model to have. We also call this uncertainty. You should always be skeptical of any model that doesn't also provide a measure of uncertainty. The first thing that we'll do is we will measure the square of all the errors. We square the errors for two reasons. First, it gives larger weight to larger errors. We want to err on the side of overestimating uncertainty rather than being overconfident in our model. Squaring the errors also makes them all positive, since any negative number multiplied by any other negative number equals a positive number. And this makes the errors easier to deal with. Then we take the mean of those squared errors, which equals what we call the variance. In fact, the formal definition of the variance is the mean squared error, which will come in handy in future lessons. But squaring the errors gives us a problem. Our measure of error now comes in units squared. Going back to our sleep example, we now have a list of hours squared rather than just hours. To recover our original units, we take the square root. Now our units are in the proper dimension. This value is called the standard deviation. The symbol that we use to represent the standard deviation is lowercase sigma, and that means the variance can be represented by sigma squared. And these are the two measures that we use for uncertainty. And now we can see how the mean satisfies all of our requirements for a model. To review, the variance measures the uncertainty around our best guess of the data. And that best guess is what we can call the expectation, which is y bar. And the formal definition of the mean as a model is the value that leads the sum of all errors to equal 0. So that's it for this mean as model installment of the Epidemiology of Everyday Life lessons. In the next installment, we'll learn how to use the mean to make predictions.